Next, we'll get to greatest common divisors and common divisors in general. So what's a common divisor? It's exactly what the name says. Let b1 up to bk be k integers. A common divisor of b1 and so on up to bk is an integer that divides each of them. So, for example, the common divisors of 6 and 8 are -2, -1, 1, and 2, because they divide both 6 and 8. Next, we define the greatest common divisors. There is a little annoying surprise in there. The greatest common divisor of this k integers b1 up to bk is defined to be literally the greatest among the common divisors. That's what you would expect it to be if not all of these integers are 0. And then the the extra case, 0 if they're all 0. This is a bit confusing because if all of the b's are 0, then every integer is a common divisor. But 0 is certainly not the greatest integer. So in this case, this is not being literally true that it's the greatest common divisor, yet it's called that way. And later it will become clearer why it's called that way. So what are properties of greatest common divisors? Also, let me give it a name. We call this GCD of B1 up to BK. And we also abbreviate greatest common divisor as GCD in writing. Nobody ever says greatest common divisor these days. Note that this is always non-negative. This is perhaps not clear. I mean, it is clear because the common divisors of any set of numbers are symmetric around the origin. If a is 1, then minus a is also 1. And therefore, the greatest one will also always be positive. And here it's just 0. So what are properties of greatest common divisors? Here's a bunch of properties, and you can, again, these are pretty easy to prove. The GCD of a and 0, and also the GCD of a alone, so greatest common divisor of one number, is the absolute value of a. And here you're already seeing why it's good to define it as 0 when the numbers are 0. So this equality remains true for a being 0. Next, GCD of AB equals GCD of BA. That's pretty clear from this definition. Next, if A and B and C are such that B is congruent C mod A, then GCD AB is GCD AC. In other words, in a GCD, you can always replace the second argument by anything that's congruent to it modulo the first argument. And because the GCD is symmetric in the argument, you can also do it with the first argument. Next. This is simply a consequence of part C, because B remainder A is congruent to B mod A. This is yet another way to restate part C. It's saying we can always add to the second argument any multiple of the first argument, and the GCD doesn't change. It's a bit like determinants and row transformations, where you can add to a row a multiple of another row. Next, this is really obvious. The GCD of A and B is a divisor of both A and B. It follows from the definition if they're not all 0, and if they're all 0, you can just check it. Secondly, not secondly, this is seventhly. This is saying the GCD doesn't change if I replace any of the arguments by its negative. Next, if A divides B, then the GCD, I want to say A, but really it's an absolute value of A because A can be negative, but GCDs cannot be negative. And finally, this is something for the pedants. I said K integers, K can be 0, then you're talking the GCD of no integers at all, but no integers at all are all 0, so it's 0. It's one more chapter in the story of the empty set. The most important property of GCDs, even if it doesn't look like that, is Bezout's identity or Bezout's theorem. It's saying the following. I'm going to state it for 2 integers. You can look it up in the notes for several integers. It's sort of the same argument, sort of the same theorem. The case of 2 integers is the one that ends up being used most of the time. It's saying if A and B are 2 integers, then there exist 2 integers x and y such that GCD AB equals xa plus yb. In other words, GCD AB is always a multiple of A plus a multiple of B. Or if you want, it's always a linear combination of A and B with integer coefficients. A z-linear combination, as it's often called. Instead of the proof, I will just give the very rough idea. We want to apply induction on A plus B. And since it's going to change unpredictably rather than just by 1, we better apply strong induction. But even so, it's a bit tricky because A plus B can be positive, it can be negative, it can be arbitrarily large and small. So first of all, we W log assume that A and B are non-negative, because if they aren't, we use this thing to reduce it to the non-negative case. We just replace A by minus A if A is negative, and we replace B by minus B if B is negative. So, and once we have assumed that, then A plus B is also non-negative, so we can apply strong induction. But also, for convenience, let's restate the theorem. We define ZA plus ZB to be the set of all integers of this form, xa plus yb, where x and y are integers. Thus, our claim that we're proving is GCD of AB is an element of the set ZA plus ZB. And that's a good way to restate it, because this is a whole sentence, whereas this is just a little formula. Okay, so let's try to apply strong induction. Let K and N assume as induction hypothesis that the claim is true for all, don't forget, A, B in N, satisfying A plus B less than K. We must prove that it also is true for all A and B, satisfying A plus B equals K. So let A and B be such that A plus B equals K. We want to prove this thing. And by the induction hypothesis, we know that the same thing is true for smaller pairs, or for pairs of non-negative integers with smaller sums than K. All right, how can we reduce this to a smaller case? Here, this proposition comes out to be useful. So part E of the above proposition says GCD, that this here is, that the GCD is equal, so it remains equal if we add a multiple of A to B. In particular, it remains equal when we subtract A from B, because this corresponds to U equals minus 1. In other words, B minus A here. So can we use this to reduce our problem to a smaller one? Yes, if we do this carefully. If A is positive, so if 0 is less than A, less or equal to B, then this is a pair of two non-negative integers with a smaller sum than a and b. Furthermore, we can easily check that this right-hand side also doesn't change if we subtract a from b. You can check this on your own. This is a nice little computation. So if 0 less than a less or equal to b, then we can apply the induction hypothesis to eb minus a instead of ab, because e plus b minus a is b less than a plus b, because a is positive. And this is k. So a comma b minus a is a pair of two non-negative integers with sums strictly smaller than k. And thus obtain GCD of a b minus a is in ZA plus ZB minus a. However, this is GCD of AB as we have just shown, and this is ZA plus ZB. I'm gonna restate this to make this clearer. And so we get exactly what we want. Well, how do we get to how do we get here? How do we get to this inequality, and how do we get to this one? First of all, I claim that without loss of generality, we can assume that a less or equal to b, because otherwise we swap them. When we swap them, this set doesn't change, and this GCD doesn't change because of this. Okay, now how do we get 0 less than a? Well, if a is equals 0, then this is easy to check. Why? Check it. This is really not the hard part here. So without loss of generality, we assume that a is non-zero, so a is bigger than 0. And now instead of saying if, we can say since. And so the induction step is complete, and the theorem is proved. More details in the notes. This is a nice little theorem, but you might not immediately see what it's good for, so here is a consequence of it. Let n be and m be 3 integers. Then m divides a and m divides b if and only if m divides the GCD. So the GCD is not only the greatest common divisor, but it's also the most divisible common divisor. So it's divisible by all the smaller common divisors, by all the other common divisors. And this holds even if they're both 0. Proof. So this is an equivalence. So to prove it, we need to prove the one implication and the other implication. So let's do the backward one because it's easier. If m divides the GCD, then m divides GCD divides a and also divides b. We're using the transitivity of divisibility here. And that's it for this implication. M divides a and b. Here's the interesting one. Assume that m divides both a and b. Why does it divide the GCD? Well, first of all, it divides both a and b. In other words, a and b are congruent to 0 mod m. Again, congruences come useful. But Bezout's theorem yields that, and I'm just going to copy paste it, there exist two integers x and y such that GCD of AB is xa plus yb. With this x and y, we then have, okay, so A is congruent to 0 mod m, so it's b, and so x0, we get x0 plus y0, which is 0 mod m. In other words, m divides GCD, and we're done. This is a theorem that ends up being used all the time. It's also known as the universal property of the GCD. And this is Bezout's theorem. These theorems have a couple consequences. So one of them is let SAB be 3 integers, then GCD of SA as B equals, I want to say S times GCD of AB. But again, I need to correct for the fact that S can be negative, so it's absolute value of F. In other words, if you multiply A and B by a number S, the GCD also gets multiplied by S up to sign. This is not obvious from the definition of a GCD. It might look like that, but it's not. Nevertheless, it's true, and it follows from the universal property. See the notes. The proof uses the universal property 3 times, so it's a great example of how to use the universal property. There's more theorems. Here is one that's, again, the use is perhaps not obvious, but it's useful. Assume you have 3 integers and A divides C and B divides C. So what can you conclude? Well, you can multiply the divisibilities and get this, so AB divides C squared, but that's not what we want. Instead, I claim that we have this. And this is interesting because this divisibility can be a lot stronger than both of these. In particular, it can be that these are proper divisibilities, so not equalities, but this is an equality. Here is an example. A is 6, B is 10, C is 30, so A divides C and B divides C is pretty easy to check. So the theorem yields that AB divides GCD of A comma B dot C. And this is saying that 60 divides 60. So this is an equality despite these two not being equalities. So the theorem here, and I'm leaving the proof again, which is in the notes. I'm leaving it to you. It's not hard to find. I think you can use the universal property. Well, I use Bezout's theorem. I think it's easier here. So the theorem is interesting in that it lets you swim upstream. What I mean is the following. In a way, the source of all divisibilities is the statement that A divides A. I generally think divisibility is upstream of another if the ratio is smaller than the other one. So for example, when you derive A divides C from A divides B divides C, you're swimming downstream. Because this divisibility is weaker than these two, usually. I mean, of course, if one of them is an equality, then you're not swimming anywhere. But when you're applying this theorem, you can usually get stronger divisibilities out of weaker ones. This is always good when you want to start with a weak one and with some weak divisibilities and get a strong one. You should think of this theorem. Here's another one, and this one is actually a little bit easier. Let A, B, C, and Z satisfy A divides BC. Then A divides GCD of BC of AB dot C. Again, this is swimming upstream because GCD of AB is a divisor of B. So you're having something stronger here than you have here. In a way, you're getting rid of extraneous factors from this BC. Again, I prove this using Bezout in the notes. There's other ways. And so many of these results can be extended to multiple numbers. In particular, with Bezout's theorem, the GCD will be a linear combination of the BIs with integer coefficients. See the notes for the details. In particular, this is perhaps the most important theorem about multiple GCDs. If you have two sets of integers, then the GCD of taking all of them together is the GCD of the GCDs of the one set and of the GCD of the other set. I cite the proof. I don't actually give it, but it's not hard once you have Bezout. Here is a little exercise that I'm not going to show the proof, but it's useful to know. What is the GCD of two such expressions, u to the a minus 1, u to the b minus 1? I claim that it's u to the GCD ab minus 1. Again, it's not literally true because it could have the wrong sign, so you have to put it in absolute values. Discussion. See the notes. Currently it's exercise 341, I think. For the solution, note that this uses the same argument as the proof of Bezout's theorem. So you have to replace AB by AB minus A. So you do a strong induction. Oh, I should say that A and B are non-negative integers. This is exercise 341B. So you assume that A is less or equal to B, you assume that A is positive, and then you subtract A from B and argue that if it was true after the subtraction, it's also true before. If you look at the homework, this is very similar to the Fibonacci exercise that says that GCD of FA, FB is FGCD of AB for the Fibonacci numbers.